This is Fermilab, a Department of Energy national laboratory near Chicago. It's the starting place for the deep underground neutrino experiment, DUNE, powered by the Long Baseline Neutrino Facility LBNF. The experiment begins with Fermilab's accelerator complex, which moves protons close to the speed of light. It's all part of an effort by more than 1,000 scientists from around the world to figure out how tiny particles called neutrinos work, and what role they play in the evolution of our universe. Neutrinos are the most abundant matter particles in the cosmos, but very hard to catch. Trillions stream through you every second without leaving a trace. At LBNF, the beam of protons will smash into a target, creating the most intense beam of neutrinos in the world. Scientists will collect data to measure properties of neutrinos close to the source and again far away. Neutrinos change as they travel, so scientists are sending them straight through 1,300 kilometers of rock toward the DUNE detectors at the Sanford Underground Research Facility in South Dakota. The detectors can also look for the birth of neutron stars and black holes by catching neutrinos from exploding stars. The 1.5 kilometer deep detectors will be filled with 70,000 tons of liquid argon, making them the largest neutrino detectors in the world. As neutrinos interact with the cold liquid, they create a shower of other particles and light. Those particle tracks are then picked up by electronics and transmitted as data to the surface. The information will be analyzed by scientists at collaborating institutions in countries around the world. They'll use this data to solve unanswered questions about neutrinos, and maybe even figure out why matter exists. Things like planets, stars.
Hey. Are you and Tom?
All right. So sorry, I'm at home. It snowed last night and it's kind of early, so.
Oh, yikes, yeah. No, that's fine. There was I'm actually in Atlanta for a conference.
Okay.
Right now, and there was some tornadoes over in Mississippi last night.
Wow. No,
so
I haven't heard the news yet.
Did quite a bit of damage in some places, and unfortunately some people died as well. So it's crazy weather out there.
I have some colleagues in Mississippi. I've got some people at Ole Miss and one at Jackson State.
So yeah, I think Ken is actually down there right now. They're doing a Bell 2 Masterclass, so they were yesterday. And so I emailed him this morning. He said it was south of where he was. So, but still, it's, yeah.
I was doing a different outreach program for this ACT-SO program for the NAACP, and there was one student doing tornado statistics with machine learning. And
oh, wow.
She had said that she noticed that tornadoes tend to hit cornfields. And I said that we have to be very careful to not come to the conclusion that we should all move out of our cities and into cornfields.
Right.
Hello.
Hello, Laura.
Hello. Sorry, I was having audio problems there for a minute. My computer connected to some non-existent speaker, but I'm here now.
That's always fun. Coming through loud and clear.
Okay, this is my first time doing this, so I'm going to be leaning on you guys for help.
Oh, yeah. No, thank you for doing this. This is exciting. It's great to have two of you here. So it's an extra special treat.
Yeah. Like we find that an hour is way too short and just way too easy to talk about. I mean,
it goes by quickly.
Yeah.
So I think we just have one group from looking at the data in Constantine. From what I can tell, it looks maybe they're still working there. But we are a couple minutes, I guess, before the top of the hour. But it looks like, I'm guessing the group from Kolkata did not materialize. And I think that it was, and that doesn't surprise me from some emails that went back and forth. So I think this is just the Constantine group.
Where is Constantine?
In Algeria.
Oh, okay. So it's daytime for
they can tell us more about where they're from, I guess. I'm just going by what it shows on here. So yeah, truly the international nature of particle physics comes through in these master classes as well, which is really cool. It's probably afternoon. Oh, go ahead. I'm sorry, Tom.
Yeah, I might drive in for the afternoon when it's snowing now. And you might not see that much because it's all snowy out the windows up there.
It looked like, I was looking at the radar earlier, it looked like you're kind of on the border of rain and snow.
Mm. It rained last night, but it's snow now.
No, it's snowing. Okay.
Roads probably aren't all that great. It's not too bad, but it's also early.
It's, we have had, in Minneapolis, a ton of snow this year. And so it's something I'm really sick of at this point. So it feels good being down here. I'm in Atlanta, like I mentioned, and it's in the low 80s for highs, Fahrenheit degrees, that is, of course.
Climate change.
A sip of water here too.
I like your, is that an RF cavity, Tom?
Yeah, I just got it off the media site.
Yeah,
Picture
I should have gotten one of the neutrino horns. Those are cool.
I have one of those. But I felt bad because you would be the one who would have to talk about it. And then it wouldn't be on the screen.
Yeah. Well, I just have MINERvA.
No,
That's great.
That's a great picture as well.
People might not realize just how big it is and what it looks like. So it's perfect.
Sure. Oh, there we go. Hello, everybody.
Hello.
Excellent.
We need to hear your sound. There you are.
Oh, there. Hello.
How are you?
We can see you and we can kind of hear you.
Okay. How are you?
Oh, we're great. How are you?
Yeah.
We are students from Harriet High School, and we are representing Algeria from Constantine.
All right. So you're kind of breaking up a little bit. I heard you students from, and then I heard high school. And so I don't know if there's a microphone that you can speak more directly into.
Fortunately, we don't have We are trying to fix the problem. Just a few minutes.
Okay, it's much better, by the way, now.
Thank you. I repeat, so we are students from Harriet High School, and we are representing Algeria from Constantine.
Excellent. Well, good afternoon. It's afternoon there, right?
Yeah.
And thanks for joining. Maybe we can go around and do some introductions. So my name is Shane Wood, and I work with a program called WorkNet in the United States, and that's where I'm based. We work with teachers, physics teachers and their students to bring 21st century physics, including particle physics, into high school classrooms. And we also work to support international master classes, of which this is part of. And been looking at your data, and the data looks fantastic. And so I'm really looking forward to talking about that. And we're going to also we're going to look at some data, and then we're going to have some Q&A, question and answer time at the end. So make sure you get your questions ready for both Laura and Tom. I'm lucky to be joined by two fantastic scientists, Tom Junk and Laura Fields. And Laura, you're one of the co-spokespeople for the MINERvA experiment as well. So so that's fantastic. So welcome to both of you, and thank you for joining us. I'm going to have them introduce themselves a little bit more, and then we'll go ahead and dive into the data a bit. So Laura, do you want to go ahead and go first. Introduce yourself.
I want Tom to go first.
Oh, Tom. Okay, that sounds good. Since this is your, yeah, fair enough.
That's fine. Okay.
Go ahead, Tom.
I'm Tom Junk. I'm a scientist at Fermilab. I have worked at other labs before too. I was a grad student at SLAC and worked on an E+ E- collider, and then off at CERN for a much bigger E+ E- collider. And then I worked at Fermilab on the proton antiproton collider. And now I work on neutrino experiments. So the long baseline neutrino experiment called DUNE, which is the biggest one ever, although there's competition coming from Japan. And it's similar to what MINERvA does, although MINERvA is blazing the ground for neutrino interactions. And you'll find all about that.
All right. Thanks, Tom. All right, Laura.
Hi, everybody. My name is Laura Fields. I'm a professor at the University of Notre Dame in the United States, which is about 2 hours east of Fermilab, where Tom is. 2 hours driving. So I've, like Shane said, I've been the co-spokesperson of MINERvA for about 5 years. So that's just sort of a strange word for leader. So I've been the leader, or one of the 2 leaders of the sort of 75-person collaboration for 5 years. I was a graduate student, like Tom, on an E+ E- collider, which is where we collide electrons and anti-electrons together and do physics with them. But then about 13 years ago, I switched to neutrino physics as a postdoctoral researcher and started working on MINERvA. So I've been working on MINERvA for about 13 years. So you've been playing with today.
Direction. And this goes from negative 1,400. Here is 0, and here is 1,400. So maybe students, do you have anything prepared to say or regarding this data?
Not really, but we can say that the interaction is in different directions. We have axis, y-axis, and the z-axis. Yeah. And we're seeing like it's 0. The value in both of the x-axis and the y-axis is 0 because it is going in the direction of the z-axis. Yeah.
Okay, so you're saying that the net momentum is 0 in the x and y direction?
Yes, the peak.
The peak. Okay.
Yeah. Yeah.
Got it. I didn't. It cut out a little bit, and so I didn't quite catch up. But no. All right. Do we see that same thing for the y direction, or excuse me, the z direction?
No, it's not the same. Especially for the z-axis. We have values, like real values.
And so I'll maybe turn it over to our moderators if they're. Oh yeah. I'm sorry. Go ahead.
For example, in the PZ, we have the peak is 4,500 MEV over C.
Excellent. Does that surprise you, or does that make sense that is a non-zero?
It was expected coming in because it's direct to the Z axis. Yeah. So yeah.
Okay. All right. And I do have this little. Maybe you saw this little drawing of the situation, if this looks familiar. So you're right on that these muon neutrinos that are coming into the interaction are zipping along mainly in that z direction, right? And then so the x and y directions are perpendicular to this interaction into and out of the screen here. So great. All right, I'm gonna go back to the data here, and I don't know if Tom, do you have a question for the group?
Actually, I have a comment on some of the discussion that's already been happening.
Excellent.
This is great. This is wonderful. But we physicists are nitpickers, and we like to get at the last little bit of everything and try to understand what's going on. And the first thing I would say that Shane said right at the beginning, your data look great, which is actually true. Your data do look great. But in a real experiment, you don't have someone telling you that your data look great. What you have is data from your experiment, and you need to understand what it's telling you. And it's nice to have experienced people who have seen data like this before and tell you that this is the way the data is supposed to look. But when you take the data for the first time and you've taken the data for the first time, you don't know what the data is supposed to look like. And it could have some surprises. And there might be something that we need to learn from it because there's something that we didn't predict very well or at all. And some of the things that we could tell you stories from the early days of neutrino physics where people were concerned that maybe energy and momentum weren't even conserved. So back in the early days, like the 1920s, when they were looking at beta decay of radioactive atoms, the energy spectrum, so they were plotting energies and momenta just like you are, of electrons coming out of radioactive decays. And the momentum and the energy didn't seem to add up. It was more random than they were expecting from a decay. So people thought, well, maybe energy momentum's not conserved, or maybe there's some mystery stuff that's getting produced. And Wolfgang Pauli was on the side of the mystery stuff. And he said, well, maybe the mystery thing is a neutrino. And that's how we got the proposal that the neutrino even existed at all. But here we are doing experiments with neutrinos, and maybe there's more mystery stuff. And some of the reasons that they proposed mystery stuff is because these distributions had widths and means that they didn't understand back in the 1920s. And maybe this is something we can do here.
One of the funny things about Pauli is that when he made that prediction that there was a neutrino, he said he'd done a terrible thing and predicted a particle that can't be detected. So you guys have proven him wrong today. So it's a good thing that Wolfgang Pauli turned out to be wrong, because detecting neutrinos is really fun.
So one thing you can ask about some of these distributions to see if they make sense is, say, X and Y, they kind of look like each other. Say if we don't understand, well, the mean is 0. So that's a nice number that you think that we could easily understand, but the width is a mystery number. But how about the X and Y widths and means? Are they the same or are they different?
X and Y, they are the same, yeah.
Right. So
And
do you
even-
expect that from the experiment, or is that something that's telling us about physics? Is this just telling us about the experiment?
No, it was expected because it's directed to the z-axis, and there is like the symmetry. There is also the symmetry. Yeah. So we have also delta x and delta y. When we calculated it, it's same. Yeah. So it's
Right. So
So-
since this experiment's symmetric around X and Y, then you expect these distributions to look the same. And if they don't, then there might be a problem with the data. So that's one way that we can check if the data makes sense, is if it obeys the symmetries that we think that it should have. So
Yeah,
even if we don't understand everything, then maybe we could understand that part. Okay. I think people had asked about PZ first because it's your top one. So you said you expected the large mean. So what makes you expect it to have a non-zero mean? And why does it have this funny shape?
sorry, we couldn't hear you. Can you repeat?
Yeah, so what you had said that you expected it to have a large mean and that this was expected. So what makes you expect that? And is 4,500 or 5,000 about the right number, or is that, why isn't it a million? Why isn't it closer to 0, or aren't there negative ones?
Not the exact value or the number, but just it's like overall, we expected that it's not, well, first it's not 0, the value is not 0. And we have like big number. We
A big number. Yeah, it's got a big
Yeah.
number.
Mhm.
Well, we do know something a priori about the neutrino beam because we made it at the lab, and we have an idea of how fast or how much energy the neutrinos have when they're coming down the beamline. But we have to simulate that with the program. And Laura is actually one of the experts in simulating those things, so she can describe that. But it's not just, so this is the energy of that muon plus, or momentum of the muon plus momentum of the proton. So it should add up to the momentum of the neutrino if everything's conserved and there are other things that we're not seeing. But if we compare this with the predictions of the neutrino beam momentum spectrum, do you expect this to be the same or different? Is this a good representation of the neutrino beam momentum spectrum? Or are there other effects that are going on? Yeah. So are we measuring the neutrino momentum spectrum with this? This is the observed. So what sorts of things are going into your measurement? Because you had to select events, right? You had some signal and background.
May you repeat, please, your question? Because our connection.
Yeah. So what went into your measurement? You had some signal and background. You selected events that looked like they had a muon and a proton. What sorts of events did you throw away?
Oh.
You threw away some events, according to the instructions, I hope.
Yeah, we had like slices, and some of them were signals, and some of them were backgrounds. But we didn't care. We neglected backgrounds, and we only cared about the signals. Yeah,
right.
You know,
what did the backgrounds look
like? Proton and muon. Sorry, proton and muon.
Yeah. So what the backgrounds look like? They're events with other stuff, right? If you have a proton and a muon, that's great. That's signal, and other stuff means it's background, right? So if you hit carbon nucleus really hard, you might get more stuff than if you hit it gently. And sometimes these neutrinos have lower energies, and sometimes they have higher energies. There's a whole spectrum of neutrino energy. And the ones with low energy might be more likely to give you a signal-like event, and the ones at higher energy are more likely to blow the nucleus apart and be background. So you might expect that to bias your distribution here, is that if the true spectrum of neutrinos is flat or goes off to very high energies, you might only see the low energy part because you selected the signal events to have only a muon and a proton. So this shape, is this the neutrino beam energy momentum spectrum, or is this something else?
No, it's not something else. It is the momentum spectrum.
Yeah, so it's carved off on the high side because you selected signal events, and there might be even higher energy events that aren't in this histogram because we selected them. And on the low side, there's another effect going on the low side. Maybe if Shane could pull up the cartoon.
Yeah.
I really like this cartoon. So people are excited about not only about this complicated nucleus, but we're excited about neutrino physics. And notice this W. Maybe you can move your cursor over to the W. That's
I'll zoom in a little bit too.
Yeah. That's back in the 1970s when people were doing neutrino experiments for the first time. They didn't know much about these W things. And these Ws are amazing things. They change one particle into another particle. They're the only particles that do that. And they're really heavy and they're really hard to make. But studying the properties of the W is kind of interesting and fun. And when they made the W for the first time in like 1982 at CERN, they found out that it weighs about 80 times the mass of the proton. And it's really, really heavy. And it's really hard to make them because they're so heavy. But they get exchanged in these little virtual things. And it turns out that low energy neutrinos have a harder time exchanging a W than a higher energy neutrino because it's easier to put some more energy into that virtual W than it is at higher energies than lower energies. And you go back to your PZ plot.
Yep.
So it turns out that the interaction rate at the low side drops to 0 just because you can't make any W's and exchange them. And on the high side, it's carved out by your vet selection. So we've got two effects going on here that make this distribution different from the neutrino beam energy. So when Laura runs her programs and generates all kinds of neutrino beam energy plots, we got two shapes. We got the ones that we expect to see in our experiments. We get the ones where the neutrino beam energy or momentum is plotted.
The shape of this distribution is sort of broadly similar to the shape of the neutrino beam. You see this peak here, but yeah, there are a lot of things like Tom say that make them slightly different. So that's what a lot of us neutrino physicists spend a lot of time doing, is trying to go from what we see in our detector, like what you guys have plotted here, to the actual neutrino energy. And it's a complicated problem.
All right, great. So maybe, I don't know if we focus down here in the X direction. I know that the students said that they expected the mean to be about 0, but was it 0 in every single case?
No, it's not.
And did that surprise you?
No, also no. It's expected as well because you know, like it's when the neutrino goes in the direction of the z-axis, it's not like directed precisely. It can like derive, so it causes the delta and the.
So are you saying that the neutrino coming in, it's not exactly going in the z direction, it has a little bit of x and or a little bit of y?
Yeah, and that's because of the quantum.
Okay, great. Is there anything else that could also give us
Effects.
non-zero values?
Did you say that the neutrino had a bit of X and a bit of Y, or this is the muon and proton sum?
Yes, so yeah, that's a good question. Were you saying students the neutrino had a bit of X and a bit of Y, or the proton and muon? Or both? Or all three, I should say.
So you didn't see the neutrino, you saw the proton and muon, right?
Right.
But maybe you're inferring from energy and momentum conservation that any imbalance in the X and Y must have come from the neutrino, or maybe it comes from somewhere else. You mentioned the word quantum. So how does this quantum stuff come in? Or I assume that's part of the materials that you read. So if the neutrino had some X and Y momentum to begin with, that wouldn't be very quantum, would it? It's just a classical conservation of energy and momentum that you would see in your observed proton and muon.
Maybe it's the momentum of the proton.
The proton on the neutron. Okay. Maybe you could pop up the cartoon again.
Yep.
And get the students to explain. So what are you saying as the px and py?
Shall we explain the interaction or what?
Yeah, or explain what you meant by quantum, or explain where the momentum goes. So you observed the proton and muon momentum px is the sum of the px's of the proton and the muon. And you had said, I think, that we could ascribe this to the px of the muon neutrino, which is one hypothesis. And we're going to ask you how to test that hypothesis pretty soon. But there's another hypothesis. You mentioned quantum. So the first hypothesis that the neutrino was the thing with the px momentum that wasn't 0, but averaged to 0. And that's not very quantum. But you said something about quantum, so maybe you should explain what you meant when you said that.
Because there is an interaction between the muon neutrino and the neutron, so
yep.
That's why it's
Mm-hmm. But is the neutron at rest, or is it moving, or what?
So this neutron here, before the interaction, is it just sitting there at rest? Or might it be, go ahead.
No, it's moving around.
Okay.
So that's where some of the non-zero px and py is coming from, right? Because that neutron had some non-zero px and py, and we have to conserve momentum. So the momentum before the collision has to equal the momentum after the collision. And the neutrino probably doesn't have very much momentum in the x and y direction, but that neutron probably did. There's another thing that can go in here. I don't know if Tom and Shane normally talk about this, but do you think we can measure px and py perfectly?
Approximately, we can get a value approximately, like the px. When we calculated it, we found 200 mega electron volt over C.
For the
around this, not just a number. So it's not precise. It's approximate. Not find the exact.
Yeah. So these distributions are not exactly at zero because we didn't start with exactly zero momentum, but also our detector is not perfect. It won't make a perfect measurement. So even if the px and py of an interaction were exactly zero, we wouldn't necessarily measure exactly that because our measurement is not perfect.
Exactly. Yeah. It's not precise.
Excellent. All right.
Back on the distribution of momentum of the neutrino. So Laura had said that we're pretty sure that the px and the py of that neutrino are small, but neutrinos are hard to make, and they're made in a beam of other particles that decay, and they decay into neutrinos all over the place. And they go in all directions, but we focus our beam so that most of it goes at the detector. But even then, it's got some spread and width to it because it's so hard to corral and focus neutrinos. So how would we be sure that the px and the py are small? What's one way that we can set it up so that we can be sure of that?
And you're talking, Tom, about the Muon neutrino, right?
Neutrino, yeah.
So how can we make sure that the Muon neutrino has a small px and a small py?
They can't be more than the radius of the ion. Exactly. If it's more, like when we calculated also, we found that the radius of the atom is around 2.7 Fermi, and yes, when counting the delta, that we found that it's 1.5, so it can't be more. If it's more, there will be no interaction.
Well, the nuclei are very small. That's true, but the detector itself is kind of big. You can see a picture of it right behind Laura.
And there it is.
The beam shoots at it, and you'd imagine that if a neutrino is coming in at some angle, it may still hit the detector because the detector is so big. And then you'll hit some nucleus inside the detector. And the nuclei is super small. But what's one way that we can make sure that the px and py are small? Maybe this is a little much for on your feet, but one thing you can do is put the detector far away from the neutrino source. So if the detector is far away, then all the lines you can draw from the neutrino source to the detector have very tiny angles. And that way you're sure that all the px's and py's are small just because the angles are so small. Now, MINERvA is not that far away from the beam source. It's right up near the beam source. We've got other experiments where the detector's really far away.
Yeah. Well, it's like, order of a kilometer away from the beam source. It's not that close. Yeah.
Right.
Yeah, close is all relative, isn't it?
Right.
Well, maybe we should, I don't know if we maybe should move on to some question and answer time to see what questions the students might have for the physicists, if that's okay.
Didn't quite, well, I guess they were getting at this Heisenberg thing, but I guess they should know that from the materials, since we're poking at all the alternative explanations. In fact, that's important, is that if you want to prove something true, you have to rule out all the other explanations.
Good point. Well, we could always come back to that more specifically, the size, but maybe we should just at least give an opportunity for the students to ask some questions before. I don't know exactly their timeline. So do you have any questions, students, for either Laura or Tom? And this could be about your data. It could be about particle physics. It could be about physics in general. It could be about science in general. It could be a day in the life of a physicist. What's it like? What was your educational, how did you get interested in this? Anyway, I'll let you ask the question.
Yeah, when doing our research, I was asking, I want to ask you a question. We were studying the interaction between neutrino and neutron, but what if the neutrino interacts with the proton, or what will, how the interaction will be, what will happen?
Were you, Laura or Tom, were you able to hear that? It broke up for me.
Yeah, I think I got it. So
Okay.
you guys were studying neutrino interactions with neutrons, and you're asking about what happens when a neutrino interacts with a proton. And actually, those do happen a lot in MINERvA. So some of your backgrounds were probably neutrino interactions with protons. When you have a neutrino interacting with a proton, sort of the only allowed interactions are more complicated interactions than the one you were looking at. So it wouldn't make a proton and a muon in the final state if you had a neutrino interacting with a proton. But actually, we can flip our beam so that instead of making neutrinos, we make antineutrinos. And if we have an antineutrino beam, then the interaction that you were looking at, quasi-elastic interactions, will always happen on protons. But in that case, we have a neutron in the final state instead of a proton. So you could have done something very similar to what you did today, where you looked at antineutrino data and you looked for a muon and a neutron. But neutrons are much harder to look for because they're not nice, clean tracks. They're like little tiny blips of energy somewhere in a detector. So yeah, neutrinos do absolutely interact with protons, but the interactions look a little different than what you looked at today. So we wanted you to concentrate on something fairly simple. So we had you look at neutron interactions.
It's a great question. Another question? Go ahead.
It's a question about one specific fundamental particle. It's about the W plus and minus. I would say we say that W boson is a fundamental particle, but we also say that fundamental particles do not decay, but W plus do decay. How?
Did you say decay? I didn't quite understand the end of that question. W bosons do what?
They go in two parts. Two smaller, I'd say, particles. 2 points. Yeah, the parts. Yeah.
I don't think I'm hearing this clearly. Tom, did you get that question?
I think she's asking whether fundamental particles can decay or not, and use the W boson as an example.
That's what I caught as well.
Okay, yeah. Fundamental particles can absolutely decay. Most of them do. Most of the fundamental particles are not stable and they don't hang around for very long. So there are a few fundamental particles that you and I are made of. Do you know what those particles are that make up the world around us? So what particles are atoms made of?
And down an electron.
Yes,
Did I hear
exactly.
that? Yep.
Up, down, and electrons. Sorry, I think we had an audio problem there for a minute. Yeah, so up, down, and electrons make, up and down make protons and neutrons, which are quite stable, and electrons are quite stable. So those don't decay. And so that's the reason that our world is made of them. But when we create high energy collisions in the laboratory, we can make lots of other kinds of fundamental particles. There are, I think, 17 of them total, but most of them are short-lived and they decay very quickly to the particles that you see that make up our world. So fundamental particles do decay. It's a normal thing for fundamental particles to do, just not the fundamental particles that we're used to seeing in our everyday lives.
Okay, thank you. I have another
Go ahead.
question, which is, I wonder what if the neutrino interact with the quark down of the proton? Is that possible?
Yes, that's possible. So you guys sort of you were working on the relationship between distance and energy, right? Because of the Heisenberg uncertainty principle. So the size of the object that a neutrino can interact with is related to its energy. So very low neutrons will interact only with the be able to
This is Fermilab, a Department of Energy national laboratory near Chicago. It's the starting place for the deep underground neutrino.
It was fantastic, and so I'm really looking forward to talking about that.